the whole idea of today's lecture is solving some problems, specific questions on chapter 1. So it could be a good opportunity for us to review what we've learned and also prepare for the exam. So for today's lecture, it's 5 questions. So I'm gonna first we talk about the question itself, and then you guys try to solve it. On the way, I'm gonna write some of the equations to just give you a hint. So in case you need to know where to start, so that would be a good way to look at it. So the first question is an industrial question. It's a sort of a practical application of what we've learned. It's about chromium in industrial processes. So historically, we have chromium in many industrial processes, such as leather tanning or metal plating. So when it's in water, in mildly acidic, it's normally in the form of either bichromate or dichromate. So these two. So, and these two species are in equilibrium through this reaction. We have the Gibbs free energy per mole at the standard state for all the individual species, also the same for the enthalpy. So the first part of the question is basically you calculate the equilibrium constant, what's the K value at 25 for this reaction. So pretty straightforward. So roughly every 20, 30 seconds, I'm going to write down one of the equations. That could be just a hint. So basically, we have to use this equation. We have equilibrium is at 25. So this is basically what we have. And then rearranging a little bit, then we know how to use individual G values at the standard per mole to get for the reaction. It was basically that stoichiometric coefficient GI0, what you have on the paper. So we know negative values for the reactant, positive for the product, for a balanced reaction. So this reaction is already balanced. So we have that stoichiometric coefficient. Calculating delta G, one source of error could be this value is basically in kg, but this one is in joule. So you have to make sure that the unit, they cancel each other. So this would be minus 8.58 times 10 to the power 3 joule per mole. And then the other one is basically temperature is in Kelvin. So 298 Kelvin. If you look at the unit, they would be just canceling out. So what you get here is 31.9, roughly. So which means this reaction, most at equilibrium at 25, most of it would be in the form of dichromate. So the reaction is leaning towards the product. So basically the ratio of this guy to the power of 2 would be around 40 or 31. So that means it's mostly dichromate in the system. So now we want to do the same thing, equilibrium at different temperature. And we had some equations in the previous lecture. Or you can basically think about, can you use something similar to this to get to the K value at 50? Can we use this one? Change the temperature, right? So you're giving H values. And in the previous lecture, example 4, I guess, you saw that delta G0 is temperature dependent. But delta H0 and delta S0 is not temperature dependent. So basically you bring that T factor into that delta G equal to delta H minus T delta S to get to delta G at 50. But to do that, you need delta H and also delta S, but you don't have any information about delta S here. So the only way you can do that is using Van Hoff equation. So surprisingly, if you use this equation by just taking the same delta G here, the value is not that far, just by accident, that far. So to do that is basically a simple Van Hoff. So very good point. It's temperature dependent. So ln K2 at the second temperature is equal to delta H R0, a non-temperature dependent factor, R 1 minus T1, 1 minus T2. I think the rest should be pretty straightforward. What should we do next? Exactly, this one. This is given. T1, we could use room temperature because we have also the K value. So T1 and K value, we already have it. So basically K2 and then T2 would be what we're looking for. T2 is the temperature given. K2 is basically what we need, the equilibrium constant. And similar to delta G for a reaction based on the species is basically the same. Delta H for the reaction at the standard state, the stoichiometric coefficient, and all the other things we talked about. and the rest would be basically a simple math. Similar to delta G, make sure this is in joule per mole, or you can make R in kilojoule. And T, as always, in Kelvin. What kind of reaction is this one? Exothermic, endothermic? Exothermic. So it exhausts heat. So that means if you increase the temperature, it's against the progress of the reaction as it's written. So that's why the K value is also going down. So when you're at a higher temperature, so this is start leaning towards this way, more bichromate then. Okay, pretty straightforward. What we did was basically using some of the information we had about the species, which was G0 and H0, to talk about a reaction. We know how to go from species to reaction. And then we did for one temperature. Later, we did it for the second temperature. And as we mentioned, this is basically a temperature independent. And this factor is basically temperature dependent. And this is the way it's connected to temperature is basically that factor. So if we had S, delta S, and delta H, then it could be T or delta G. I think example 4 of the previous lecture. The second question is basically sort of not quantitative, but more analytical. So it requires you to think about what we've learned and how we can basically use it for a real world application. So here it's pretty simple. We have a reaction. We have some tools in the lab. And we want to know one important feature of that reaction, which is delta H standard for the reaction using whatever tool we have. So to give you an idea, what we have in the lab is some of the equipments, an instrument that can first accurately measure the species concentration. Then we have also a heating system that can measure and control the reaction temperature, sort of applying heat and then measuring it as well. So we want to do two things: design an experimental procedure, also do data analysis. We're looking for a pipeline, how to do that, to eventually get delta H of this given reaction. Very practical example. So you're in the lab, you have these tools, and you want to do first data collection and then how to do data analysis. Where do we start? We have to have some equations in the back of our mind that would be basically the one that we're looking after or we are trying to play with. We need delta H. So delta H must be a part of an equation. But it can't be any equation because you can connect it to delta G and delta S, but do you have anything to calculate delta S experimentally? So this is basically what you have. You have a unit that can increase the temperature of a solution. It can also read the temperature. You have also some tools, some instrument in the lab that at any point, if you want, can calculate the concentration of A, B, and C. So what is the equation that you want to have that as a core and then play with what you have in your toolkit to calculate delta H? So Van Hoff could be a very good starting point. So Van Hoff could be the core because it seems, and now we need to think about how we design an experiment, collect data, and do analysis to get to delta H eventually. So basically, you're using your ability to directly measure or directly provide input for these two. Then you're also at two different temperatures. You establish equilibrium. So basically, you have the concentration of each. You can calculate K, bring it into this equation, and do delta H. So that's is logical, and that's good, but it could be perfect. So basically, what you're doing is relying on 2 points, 2 data points, and then drawing a line between 2 points, and then it's always linear. R2 is always equal to 1. So a modification to what you mentioned is basically instead of 2 data points, we do a lot of data points. So we extend it basically. So the procedure would be first, we prepare a bulk solution. So we're basically adding A and B to the system. So basically we dump some A and some B to the system. So then we try to establish equilibrium at a given temperature. So basically what we do is we mix them. I'm trying to use like an executive kind of language that we use in the lab. So we mix them at a controlled temperature. Let's call this Ti. So one temperature, we have the ability to do that. And then we let it equilibrate. And now we use the other tool we have, which is basically measuring the equilibrium concentration. So basically what we're getting at 0.3 is the concentration of A at Ti, the concentration of B at the same temperature, the same for C. Can we now calculate K? Can we? Lecture 2? You're jumping to lecture 3. We should change the concentration to, so K, activity, exactly. So concentration, we simplify it, but now we're in the lab, we need something more accurate, and we have a tool to calculate activity based on the concentration. So the next step would be to estimate the activity coefficient based on what we've learned in lecture 2. So to estimate activity coefficients by just using ionic strength. And then we can calculate activities. So we get activity of A at T1, Ti, and so on. Now we can use it for calculating K values. So estimate K, which would be K for the given reaction. So far we have all the information. And then we get one single data point. And that data point is Ti and K at Ti. 2 data points would be enough to use Van Hoff. Well, as I mentioned, we can basically extend it for more data to have like a more accurate, more. Yep.
Are we estimating activity or are we calculating?
Calculating. Sorry, that's a good point.
Using the 3 models?
Yes, exactly.
But do we know the concentration of the whole solution? Because we would have to figure out which model to use.
Exactly. So we get this one. We calculate ionic strength, and based on the ionic strength limit, we know what to use. You could also do a trick. You can play only on the dilute side of the spectrum, all of your data points in dilute, and then you can just basically skip these 2 points. But to be more accurate, you can basically extend it. So up to this point, one very important, very accurate, and we basically use everything, all the tools we had to get to this 1 point. To do that, we basically repeat the whole 2 to 6. We don't need to make a new solution, but we rather increase the temperature, measure again. So after we repeat 2 to 6, the database is basically T1, K1, T2, K2, and so on. So the reason 2 points are not very accurate is sometimes you're at the limit of your sensitivity of your instrument. The researcher is not very accurate. You might get some random stuff in your solution. So basically by doing more data, you're eliminating all of those and not considering the outlier. So now we have a database of pairs of T and K. Yes. Yep. Mm-hmm. That's a very good point. What's that? Yep, that's one way, exactly. So there's one actually 0.4 here that you monitor the concentration. Monitor the concentration as a function of time. And then if it gets to something like this, for example, and then you make sure it's equilibrium. Or sometimes it's visually you can see it if you're lucky and that the solution is colorful, and then you know that the color is not changing. So now you have the data collection. The next part will be basically to use the equation, do the data analysis. So a common practice we do all in the lab if you're doing experimental work. The easiest way is to do somehow linear fitting. So linear fitting is one of the easiest that you could work with. You just need to rearrange a little bit, rearrange the equation because it's not right now linear. So we can write down the Van Hoff equation, assuming that we have a reference point and then calculating other points based on the reference point. So we want to calculate K at a given temperature. So that's basically what we're looking for, compared to K1. K1 is a reference point, something that we know. We know the K value and we know the T value. Then this is something that we don't know. So R, then the reference T1 minus 1 of the temperature that we are interested to calculate the K value at. So what I want to do from here, it's not very easy to play with this, to work with this equation and do the linear fitting. At least the parameters are not linear. So I just need to twist it a little bit, play with the natural log, and also expand it on the other side to eventually get something that is linear. So that's basically the next step. So I can extend the natural log first, because this is something that I'm interested in. This is something that I know, so it's a constant. Then the same thing here, delta HR RT1 minus delta H R0 R1 over T1. Or again, rearrange it a little bit. So it would be ln K, something that I'm interested to know. On the other side, all the known values, or all the values that I have information about, ln K1 minus delta HR R1 over T. So now we made it sort of linear. How this is linear? How this is in the form of y equal to ax plus b? Because that's the linear form we're looking for. Okay, so this could be our b. And 1 over t is the variable. So basically this could be minus delta h would be a. So this is our x. This is our y. So we made it in the form of y is equal to ax plus b. So the only twist that we need to do is basically the database that we have was TI-KI. Now we need to basically make that 1 over TI to ln K. And this would be TI. Yep. Sure. Yeah. Yep. So now if we switch the database from this one to this one, then we can basically plot, and then whatever we're interested is in the slope of that linear curve. So basically what we're doing is plotting ln K over 1 over T. Is it like this or like this? Increasing? Decreasing? It's a negative slope? Exactly. So it could be either. So basically, it could be either this guy, or it could be this one. And the interception also gives us the information. So this would be for an exothermic. So that means delta H is already negative, so this would be also negative. Then the slope would be a positive value. So this is exothermic, and this is basically endothermic. And then the slope of this one is basically that A term, which would be minus delta H R over R. So we have the slope from, let's say, that Excel sheet that we have, and now we just basically make that equal to the value to get to that delta H. So as we mentioned, it can be done by 2 points, but right now we have more than 2. So each data point here is one experiment. So we might have a similar question in the exam that you basically designing an experiment, but first you need to find the core equations that you want to play with. Based on that, collect data logically, as we did here. Do a little bit of analysis on the data, for example, going from concentration to activity, then K, and then use K in the equation. And then later, data analysis and data representation, and how we can use the feature of that data representation, which is the slope here, to get to what we're interested to know. So by doing this procedure, you can basically calculate delta H for any reaction, as long as you have the ability to calculate the concentration of the species. So we talked about, I think lecture 3, we talked about, or lecture, 3, the K value of the overall reaction based on the K value of the individual reaction. So it was basically a product of the individual reactions. But we never talked about the Gibbs free energy. If we have for 2 reactions, like this one, for example, how do we get for the overall reaction if we can make the second reaction? So this part would be very straightforward. So we're going to solve it together. So right now what we have is we know delta G of these two, and we know reaction 3 is simply the combination of the 2 reactions. So we want to see how delta G is related to the delta G of the individuals. So what we did for K was we do the same thing here. We individually look at the reactions and then see how 3 compares to the other 2. So first we know reaction 3 is basically reaction 1 plus 2 without any modification. So we individually look at reactions. So reaction 1, delta G R of reaction 1 is basically, the stoichiometry coefficient GI, or this would be minus A GA minus B GB. Oh, these are not necessarily standard, so we just don't need to work with the standard. Plus CGC. Same thing for reaction 2. Delta G of reaction 2 would be minus CGC plus DGD. And now only looking at reaction 3, we see that delta G of reaction 3 is equal to minus A GA minus B GB plus D GD. So how does delta G3 compares to the other two? Yeah, so sum of the other two. So R delta G, or it seems delta G R3 is equal to delta G R1 plus delta G R2. And as K, we can also test it for more complicated reactions, but if you do that, trust me, you get to this point that if R overall is a combination of the individual Ri, then what we saw for K was the product, but here for delta G of R is a combination of the delta G of the individual. And the same thing for also delta G at the standard. What happens if we reverse the reaction then? For K value is 1 over K value. What happens here? So if we reverse the reaction, what happens to delta G? Yeah, so the opposite sign. We'll see that later, but for K, we saw it's 1 over K. So it's another useful tool that later we can also implement it. If we have delta G for individuals, then we can basically get to the overall. So part B is asking, in the lecture, we show that K overall is the product of the K values. So here we want to use this information from part A to basically prove that K3 is equal to K1 times K2. What we did in the previous lecture, or in the lecture, I think lecture 3, was we established the same thing. We did K1 for reaction 1, K2 for reaction 2, K3 for reaction 3, and then we compare the three K values. But here what we want to do is basically using the same thing for delta G. So we know K3 is exponential of minus delta G 0 of reaction for reaction 3. And from part A, we can basically expand this. This would be minus delta G of reaction 1 plus delta G of reaction 2. The next part is basically we break this two exponential terms. So this would be equal to exponential of minus delta G1 reaction 1 times exponential of minus delta G of reaction 2. What is this guy? Exactly, and this is basically K2. So we prove that K3 is equal to K1 times K2, but from a different approach. So K and delta G are connected through this reaction. And if you take my other course on electrochemistry, that those two are also connected to standard reduction potential. So it's sort of a triangle, and we know how to go between the two. Between K and delta G is basically this exponential, or if we want to go opposite, that ln of K times RT, and then it would be some sort of expression for the standard reduction potential. So what we've learned from this example was how to deal with delta G for a combined reaction. So the next question would be sort of a little bit more complicated version of what we have here. So combining what we've learned about the K values and the delta G values for all sort of reactions. If we reverse it, if we multiply it. So we have the three reactions. What we want to do is going for reaction 4. So again, you guys work on it, see how we can solve for this one. First, if you guys know how to get reaction 4, let me know from the first 3 reactions. So X times reaction 1 minus reaction 2. So basically it's the same thing. So reverse of reaction 2 plus what? Okay, good. So now we want to see how we know how to deal with K when it comes to X times reaction 1. We had that before. It's K to the power of X. We know how to do it for reverse. So we want to know how to deal with delta G basically for times a factor or reverse, which is times minus 1. So just do the same thing. I mean, I'm going to do it for reaction 1 and then we go from there. So for reaction 1, K1 is basically B over A, and delta G for reaction 1 is minus GA plus GB. So for X times reaction 1, you know we're dealing with XA in equilibrium with XB. And we know K of X times reaction 1 would be, we had this before, so just X or K to the power of X. Now we just want to write down the delta G factor also. Delta G of reaction for X times reaction 1 would be minus X GA plus X GB. Or we can factor this X value minus GA plus GB, or X times delta G of reaction 1. So as you probably guessed, this would be X times the delta G of the original reaction. So now we know how to do a reaction multiplied by like a factor, how delta G is changing compared to the original reaction. So similarly, we can do for reaction 3. So Z for, it was Z times reaction 3. So K of Z times reaction 3 would be K3 to the power of Z, and delta G would be Z times delta G of the original reaction 3. So the only thing left is to deal with the reverse of reaction and deal with reaction 2. So, and at the end, we just combine all the three together. So for reaction 2, the original reaction, we got K2 D over Y, then B X, and then C over Z, and then delta G of reaction 2 would be minus Z GC plus Y GD plus X GB. We just need to do the reverse of the reaction. The reaction would be XP plus YD ZC. You know, K of reverse, basically C over Z. So we had this before, so just repeating it here, which is basically 1 over K2. And delta G of reaction of reverse of reaction 2 would be minus X GB minus Y GD and then plus Z GC, which is, this one is the opposite sign of delta G of reaction 2. So if we reverse the reaction, then delta G would be basically the opposite sign. So now we have all the individuals. So 2 from here, one was this guy. The other one was the K value here. It was this one. And also this one. So we combine all of them together. Since the reaction 4 is a combination of the individual reactions, not necessarily 1, 2, and 3, but the other forms that we talked about, then K4 would be the product of the individual K, and delta G would be just the combination of delta G. This was from problem 2. So the last step was just basically combining all the K values, multiplying them, would be K1 to the power of X, 1 over K2, and K3 to the power of C. And for delta G values, that would be delta G of reaction 4 would be equal to X times delta G of reaction 1 minus delta G of reaction 2 plus Z times delta G of reaction 3. So this is also very useful. Sometimes you have a random reaction that you don't have enough information about that reaction, but you can logically look at standard tables to find individual reactions that you can eventually play with them, either by multiplying by a factor or reversing it to eventually get to that point. And we know how to deal with the K value and also the delta G value. Okay, so the last problem, it's about disinfection of swimming pool and hot tub. So pretty straightforward. We have a resort that has swimming pool at 25. We also have a hot tub at 40, so 2 different temperatures. And we add the same total concentration of disinfectant, which is 0.2 millimolar to both. So the total that we're adding, basically distributing between the 2 species that are connected together at using this reaction. For both of them, the pH is 7.2, so the pH is fixed. So the distribution of these two, the combination of the two would be the total. The distribution is dictated by the K value, right, at equilibrium. And K value is also temperature dependent. So you might guess you get more of HOCl in one of the environment, either the hot tub or the swimming pool. So the whole idea is if you add the same amount, because the temperature is different, the K is different, so the ratio is different. And we know if the ratio is different, the disinfection factor of this one versus this one is different. So even though you're adding the same, it doesn't disinfect as much for one system compared to the other. So, and we have all the key factors for all the individual species, H, S, and G. Now we want to basically do a similar thing as we did in the first problem. First, we want to calculate the equilibrium constant. For the hot tub, we have the equilibrium constant for swimming pool. So very straightforward. A Van Hoff, we have everything. We have T1, T2, K1, K2 is missing. And delta H needs to be calculated based on basically this line. So we know first we need to use delta H, calculate delta H0, which is basically a combination of all. 9, based on the values that are given, minus 107.1 plus 0 for that H plus. This is 13.8 kilojoule per mole. And this is temperature independent, so it would be the same for both. It's just for the reaction. So based on the Van Hoff, we can calculate ln of K for hot tub. This is something that we're looking for, and then swimming pool that we have. Delta H R divided by R, 1 minus T of the swimming pool minus 1 T of the hot tub. So we have 3 out of 4. So we have the temperature of the swimming pool, which is at 298, 25 degrees C, 298 K. We have K of the swimming pool, which is 10 to the minus 7.53. We have temperature of the hot tub, 40 degrees C, and then the K of the hot tub is missing. Is it bigger or smaller? What do you think in terms of the magnitude? You have one key information so far. What's the nature of this reaction? Endothermic. So when you increase the temperature, is it in your favor in terms of going towards the product? So probably so it's endothermic. The end of the process is temperature is lower. So if you increase the temperature, so it's going backward, right? So you're expecting sort of a lower K value. So if we add all into the Van Hoff equation, then we get ln of K hot tub to K swimming pool of 0.267, or the K value of hot tub to be 3.85, 10 to the minus 8, or 10 to the power of minus 7.41. As you see, it's different than what we had. Yeah, this value comparing to this value. So it's a bigger value. So the first part was pretty straightforward, just a Van Hoff K value at a different temperature. Here, you can also use that delta GR equal to RT ln K. Because as Himanshu mentioned, this is a temperature dependent factor, but you have information about the S values. So you can make your life more difficult, but go into calculating delta H, also delta S, then delta H minus T delta S to get delta G at 40, and then delta G equal to RT ln K at 40. But Van Hoff, I think, makes it easier to just do that, but just only using delta G. So the second part is talking about a concept we introduced in the previous lecture, which is the extent of reaction. To overview that quickly, the extent of 0, it's if this is the reaction. The extent of 0 is we have only A. None of A is formed B, is produced. No B is produced. Obviously, the extent of equal to 1, all A is converted to B. So just the extent of reaction that we talked about before. So now we want to plot the Gibbs energy of reaction as a function of the extent of reaction. So from the extent of 0 to 1, we want to see how delta G is changing for both hot tub and also the swimming pool. So the first thing we have to write is basically the delta G reaction formula, what you have on the printed paper, delta G 0 plus RT ln Q. So that's what we had in the lecture 4. So, and then we can expand Q, would be OCl minus, H plus, HOCl. And then because this is overall is 2 times 10 to the minus 4, it's pretty dilute. So we can say if because it's dilute, then the activity coefficient is 1. So activity is equal to the concentration. OCl minus, H plus, and then HOCl. Because we haven't started chapter 2 on acid base, we don't care about that H plus yet. We're assuming that's fixed. The pH is fixed at 7.2. So from the previous lecture, OCl minus, we can basically connect that to the total concentration and epsilon, the extent of reaction. We can quickly test that. at extent of reaction of 0, then the concentration of OCl minus is 0, which makes sense. No HOCl is converted to OCl minus. And also for HOCl, we can do basically the other way around, is 1 minus epsilon. At the extent of 1, there is no HOCl, so all the reactant is converted to product. Also, only for this example, because it's given, the concentration of H plus is always constant. It's 10 to the minus pH. So now we can basically add this information to delta GR, would be delta GR plus 8.314. Now I'm converting basically everything to kilojoule per mole. So delta G0 is in kilojoules, so R I'm converting it to, that's basically the kilojoule term. That's why you have this 10 to the minus 3. Then T, ln 10 to the minus 7.2, epsilon, 1 minus epsilon. So now this is the core equation. What we're looking for is delta G on the y-axis, epsilon on the x-axis. So we can change epsilon from 0 to 1 logically and then calculate delta G. But now the difference between swimming pool and hot tub is the T factor. So the T factor changes for, not change, is change for swimming pool and hot tub. Anything else? Exactly. So delta G also is different for the swimming pool, as we talked about. So basically, we need to write down the same equation for swimming pool and hot tub. The only thing that is changing is the T and delta G. So we need to do delta G of reaction at 25, which is the swimming pool. We can directly use the values that are given because those values are for 25. So we can basically do minus 79.9 plus minus 36.8 plus 0. This was 43.1 kilojoule per mole. The values for delta G at 40 are not given. Well, we have K value for 40 in part A, what we calculated. So now we need to go backward. So delta G of reaction at 40, which is the hot tub, would be equal to minus RT ln K 40, which is from part A. And if we do that, this would be 45.1. As you see, different value compared to 25. So the next thing we need to do is basically inserting this value into this equation and obviously the correction for T. And if we do that, then for swimming pool, the equation would be delta G R, our y-axis, is equal to 43.1 plus 2.48 after I insert that T value and do all the calculation. ln of 10 to the minus 7.2 epsilon, our x-axis, 1 minus x epsilon. And then for hot top, this would be delta G R 45.1 plus 2.60 ln 10 to the minus 7.2 epsilon 1 minus epsilon. So we have two equations. We just need to construct a plot. An easy task if we have Excel or any other programming language that you want to use. So we know how delta G, the Gibbs free energy, would change as the reaction progressed from the extent of 0 to 1 for the swimming pool and the hot tub. And if we do that basically in Excel, this would be something like this, pretty straightforward in terms of epsilon on the x-axis, delta G for swimming pool and delta G for hot tub, just a calculation based on the equation we had in the previous page for each. And then if we basically have this one, then it would be something like this. As you see, very, very close. The profile is very close for both swimming pool and the hot tub. So what it says is delta G, the Gibbs free energy, is going from minus 30 all the way to 20 kilojoule per mole for the two reactions. We basically overview whatever we talked about in the first 5 lectures. We talked about activity, we talked about equilibrium, some of the fundamental and practical thermodynamics.